Let's take a look at this next chapter. This is strings and text files. And let me get code here. Okay. This is just doesn't have anything to do with exercise 4.1. I just picked this out so I could have something to some work with. Say we have some code here. Remember, a string is any combination of alphanumeric. So you got alphabet, you got numbers, you can have different characters like exclamation, question mark. So you can have any combination of digits. Not just numbers, I shouldn't say digits, but any combination. Now, I got my name here, David space Hayes. And let's say I wanted to separate this out. I wanted to pick apart my first name and my last name. Maybe we ask the person to input this in. Let's see. Enter name. Okay, so we got some code here. We run it. It says enter name. David space Hayes. It prints out David space Hayes. Question is, how do I separate this? How to put the first name in one variable and last name in another variable? Maybe we have an input a date. Like this. And they run it. It says input date. And we put in 09/116/2018. Press enter. Question becomes, how do you separate the month from the day from the year? Those are questions that we'll answer in this chapter. How to work with strings. Objectives. Access individual characters in a string. Retrieve a substring from a string. And that's actually how you would pick out the month, day, and year from it. Search for a substring in a string. Convert a string representation of a number from one base to another base. Use string methods to manipulate strings. Open a text file for output and write strings or numbers to the file. Open a text file for input and read strings or numbers from the file. And use library functions to access and navigate a file system. Accessing characters and substrings in strings. Substrings in strings. In this section, we'll examine the internal structure of a string more closely. You learn how to extract portions of a string called substrings. Now, this talks about the string is actually a data structure and consists of smaller pieces, and the numbering on it. Like if I had a test string 2 equals David. D would be position 0. A would be position 1. V would be position 2. I would be position 3. And D would be position 4. So it's kind of strange. It's not like what you might think. You might think, well, D is position 1, 2, 3, 4, 5, and there's 5 positions. That's not true. Now, on the other hand, it refers to the length here. The length is not like going from 0. It says if you're counting them. So here, the length of David should be 5. So if I print length of test string 2, and rerun it. I'm leaving that there because we're going to be working with that shortly. You notice it comes back and tells us 5, because there's 5 characters. Even though the numbering starts in this manner. For the subscript operator is, we got our string name, and then we got a bracket, integer expression, and then closing bracket. So for example, we said our length is 5. If I print position 1, now position 1 is actually 0, because remember the index starts at 0. That should print the letter D, uppercase D. If I print a second position, which again numbering starts at 0, so it's 1, that should print A. And string 2, 2, that should print V. So it should print DAV on separate lines. And that's what it does. It takes a little bit of getting used to, and sometimes when I'm trying to pick part of my date off, I have to number it. For example, if I know I'm going to work with 09/16/2018, this would be position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So using that setup, I see that my month, assuming I put 09 in, goes from position 0 to position 1. The day, 16, that's position 3 to position 4. And our year goes from position 6 to position 9. So sometimes when I'm working with strings, I'll actually write out an example like that so I can wrap my mind around how the programming should go. Strings can be tricky. They kind of throw you. And this talks about how you can use the -1, -2 next to the last character and so forth. And you can look at that. Oops, an index error. Our positions go from 0 to 4. So if I try to print position 5, let's see what it says. (09/16/2018) gives me an index, string index out of range. Again, it's invalid. You can't access that. If I put in -1 and try run it, you're going to see it actually returns something. So the negative doesn't mean that it's invalid in Python. Some programming languages it does. But that's what this is referring to. We got the -1, this says examine the last character. If you put a -2, this is the next to last character. -3 would be the next one over. So that's if you want to go in reverse. Subscript operator is useful when you want to use the positions as well as the characters in a string. You can use a count controlled loop. So we got a data high there for index and range, length of data. The length will return the size of it again. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So it goes from 0 to 8. And when you refer to data and then bracket index, closing bracket, this is accessing data 0, data 1, so forth. So it's going through character by character through that string. Now you could do different things at that point also. You could check if it's a certain character. So you can count how many S's or how many T's are in a string. Python subscript operator can be used to obtain a substring through a process called slicing. Place a colon in a subscript, and an integer value can appear on either side of the colon. And we got our name, myfile.txt, and so you got name 0, colon. You see what it returns. name 0:1, the first character M. So it starts at position 0 and it goes one character over. Okay, let's take a look at that then. Getting rid of all that. Going back, I shouldn't have got rid of my example. If I put in 09/16/2018, this is position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, once I've input that in, then I'm going to say month is equal to, and this is the syntax of what we want. We got our string name, colon, and then that. So I'm going to put in test string, colon, and my month starts at position 0, and I think 2 characters. Sometimes I have to play with these. I don't get it right the first time. Test string, the day starts at position 3, and it's 2 characters long. And year, position starts in position 6, and it's 4 characters. So let's print month, print day, print year. Run that. 09/16/2018. It looks like my month is working right, but my year isn't, or day isn't, and year. So what did I do with that? Curious. Almost looked like it printed something and then undid it. Let me get rid of month here. Let's see what that does. Okay, let me see here. Is it the first 2 characters? Zero, 1, 2, 2 through 6, 3, 4, 5, 6. Oh, not the number of characters, it's where it ends at. It's another language I'm thinking of. Okay, so this starts in 3. I would say it ends in 4, but I think it goes 1 beyond. So let's put 5 in. This is 6 and ends in 10. Let's see if that's right then. 09/16/2018. There we go. I just remembered the function incorrectly. So that's the way you can pick off that information. Now, there's a problem here. Besides the fact I don't have memory. If I put in 9/16/2018, well, it still comes back with something, but not the correct answer. It's assuming that the month is going to be 2 digits, which isn't always the case. There's other ways to pick apart that information. So the slicing here wouldn't necessarily be the best if it varies. Now you can test for a substring with the in operator. So if .txt is in the file name, then you do whatever. So for example, down here I can say if 09 in test string, and print the month is well, month is maybe September. Why do you think I hesitated there? Well, think about it. If you put in 1009, that'll also come back. And 10 is October. So all I can really say is if 09's in the test string, that month is maybe September. Okay, so if I run it, 09/116/2018, month is maybe September. If I run 10/10/2018, doesn't come back because that end does not work. But like I said, if you do 10/09/2018, it says month is maybe September when we know it's really October. So again, there's better ways to do it than check the month in what I'm showing. This just demonstrates the function. Data encryption is it's easy to observe data crossing network, particularly in wireless networks. Attacker may use sniffing software. Sniffing software, what is that? Well, the different forms of it. But one form is you hook yourself into the network somehow, plug into a free port or something, and you got a software that sits there and watches all the characters going across the internet or the network. And if it's not encrypted, they can see the plain text. This is when you go to a website and it says HTTPS has encryption. If it just says HTTP and you're signing in, then potentially it's just going to cross as straight text and everybody can see your password. Data encryption can be used to protect information transmitted on networks. Many protocols have a secure version, HTTPS, what I mentioned. One or more keys are used to encrypt messages, to produce ciphertext, and to decrypt cipher back to its original plain text form. And some examples they present in the book are the Caesar cipher and block cipher. Caesar cipher replaces each character in plain text with a character a given distance away. Example, if Caesar cipher equals 3 characters, the string invaders would be encrypted as LQYDGHUV. To decrypt, apply a method to use the same distance value, but looks to the left of each character for replacement value. We've got our ASCII values going across the top. Then we've got our new ASCII values down here across the bottom. It's a little bit different than you might think when you look at it. You see how not all of them are on here, but invaders, I and N aren't on here, but the V is. And V is right here, and then straight down below to the ciphertext it says Y. And you notice how they replace the V with a Y here. And you might say, yeah, but how are those 3 characters apart? Well, look at the ASCII. 118 and 121. They're a distance of 3. So that's what they're referring to. Now the ORD function returns the ordinal position in ASCII sequence. So that's what gives us those ASCII numbers you see here. Those ASCII values, that's how you get those. So this is all comments here. It gets a string called plain text. And then distance, it asks the user for a distance. Got our code. Then for each character in plain text. Now the in here is not actually looking, it's not looking for a string within a string. What it's doing is it's going character by character. So then it's taking this, it's converting it to the ASCII value. It's taking the ASCII value, the ORD value, and it's adding the distance, in our case 3. And then if it's equal to Z, which I assume is the end of the table, I'd have to go look at the ASCII myself. Then it's taking the ORD of A, so it's going to the very beginning of the list, and adding distance. Let's see, ORD Z minus ORD value plus 1. Z to... Oh, okay, I see, because there's some distance with it being at the very end of the list. And so if it uses 2 characters there, then it has to account for that. Okay, that makes sense. And then we got code is equal to code plus this. So it just concatenates the character onto our code and then prints the code out. Now going the other direction. You receive the string in. And over here, we added distance. So we added 3. Here going the other direction, we would subtract 3. But again, we have to worry about if we run across A, the very beginning. So then we kind of need to loop around to the Z's. And again, this minus here, this accounts for if I move 2 characters to the left on the A, I'm subtracting it, then that accounts for it, so I know how many to do at the very end. This just shows an example. Caesar cipher worked well in ancient times, but it's easy to break using modern computers. You can write a loop. You can sit there and write a, there's, I'm not sure how many ASCII characters there are in there. Let me see. Total of 122 looks like. So you could write a loop going from 1 to 22, and where you're doing that shift. And so by shifting it back, it's very easy to figure out with a computer program. Now, a computer program to decipher what's a valid code isn't probably feasible, but you could sit there and print out all 122 on the screen, and you can see which one's a valid one just by eyeballing it. We got a block cipher. Uses plaintext character to compute 2 or more encrypted characters. Each encrypted character is computed using 2 or more plaintext characters. Uses an invertible matrix. The arithmetic operations uses a decimal number system called the base 10. Binary number systems is used to represent information in digital computer. Base 2, this is where you got 0 and 1. 0 is false, 1 is true, or on and off, 1 being on. Also goes along with the design of the computer in terms of voltage. Other number systems that are common are octal, base 8, that goes from 0 to 7, and hexadecimal. That goes from 0 to 9, and then you have some additional ones of A, B, C, D, E, F. So you got letters in your number, so it always seems weird. And it gives you some breakdowns there. We're not going to how to translate those by hand. This will allude to it, though. Digits used in each system are counted from 0 up to that n-1, where n is the system's base. So if I had a base of 6, I'd go from 0 to 5. To represent digits with values larger than 9 with base 10, systems such as base 16 use letters. That's what I already talked about. A is 10, B is 11, C is 12, and so forth. Up to 15. Positional system for representing numbers. In positional notation, a digit has a positional value determined by raising the base to a power specified by the position. Base to a power of the position. So 415 base 10 is equal to 4 times 10 squared times 1 times 10 to the first plus 5 times 10 to the 0. And that gives you what that's equal to. And you might say, well, that's really good. 415 is equal to 415. Well, you have to think of it in terms of other bases. For example, if you had, I don't think I can type on here. Nope. I shouldn't have double-clicked that. I guess I can't type anything in there. But if you had 1, 1, 0 and base 2, it'd be 1 times 2 squared plus 1 times 2 to the first plus 0 times 2 to the 0. So whatever your base is that 10 squared, 10 to the first, 10 to the 0, you replace that with your base. If it's base 5, it'd be 5 squared, 5 to the first, 5 to the 0. Here's what I'm talking about. It always starts at 2 to the 0 clear over here, then 2 to the first, 2 squared, so forth. So this first one here is 2 to the 6. Next one's 2 to the 5th, and then 0 times 2 to the 4th, 0 times 2 to the 3rd, 1 times 2 squared, 1 times 2 to the 1st, and then 1 times 2 to the 0. And then that would give you that this in base 2 is equal to 103 in base 10. Well, here's a code to convert that. Okay, so we ask him to input a string of bits, ones and zeros, and decimal is equal to 0. We got our exponent is equal to the length of the bit string minus 1. So if the bit string is 5, for example. Let me copy this code over. I don't know if I need to switch those or not. I think I do. Yeah. So if I run this, oh. Try that. Length of bit string minus 1. You might look, it's like, well, that's a dash. Why is it counting wrong? There's a couple different dashes on these computers. So if I do that, that gives us 7. Why does it give us 7? Well, the idea behind that is 1, 1, 1. This first one is 2 squared. Next one's 2 to the first. Next one's 2 to the 0 power. Like that. So we would take 1 times 2 squared, which is 4. We'd take 1 times 2 to the first, which is 2. That's 6. And 2 to the 0 is 1. So 1 times 1 is 1. 6 plus 1 is 7. If I change that to 0, keep in mind, this is 4, this is 2, and this is 0. We would take 1 times 4 is 4, 0 times 2, which is 0, and 1 times 0, or 0, where'd that come from? 1. 1 times 1, which is 1. So we'd have 4 plus 1, which is 5. So let's run that again just to show it. Okay, so how does it work? Well, if our length, let's actually look at 101. That's a length of 3. So this length of bit string here would return 3. Then you got 3 minus 1, which is 2. So our exponent's 2. Then I come down here for digit in bit string. So it's going through. By the way, that 2 that it's giving you, if I had like another one here, would be 4. This is giving you the largest exponent. This right here is giving you this second power right here. So if we had 1, 0, 1, 1. This is 2 to the third, this is 2 squared, this is 2 to the first, this is 2 to the 0. If I look at the code, exponent should give us 3. So it always gives you the largest exponent. Okay, so for digit and bit string, so it's going through each one of these digits. So start with this first one, this 1. The decimal is equal to decimal plus integer of the digit. It's going to convert to an integer, and it's 1. Times 2 to a power, and that exponent. The decimal has nothing to do with decimal. It refers to base 10, basically. And then you reduce your exponent by 1. So instead of 2 squared, it now goes to 2 to the first, and goes on down. And how our integers convert from decimal to binary. When our algorithm uses division, subtraction instead of multiplication and addition. Repeatedly divides a decimal number by 2. After each division or remainder is placed at the beginning of the string, quotation becomes next dividend. Another one, let's see if that gives it. Another one is you just keep subtracting powers of 2. Okay. And yet again, they got this screwed up. I don't know why they can't get the format right. So let's take a look at this. We know that, we know 101 in base 2 is 5. That's in base 10. So, go backwards, we can start with 5, and it should give us 101. Okay, so decimal is going to input that in. Decimal is equal to 0. How bizarre. I think spacing is 4. 1, 3, 4. Usually it doesn't put it clear out there, it puts where it should be. Okay. Bit string's this, while decimal is equal to this. 1, 2, 3, 4. Think like that. Okay, let's run that. End of line. Decimal equals int input, enter decimal integer. This does have an extra one. 101 gives us 5. Now if I put in 5 in, it should give us 101. Okay, so that's the proper formatting of that that problem there. Well, decimal is greater than 0. And decimal integer, so I put in 5. Decimal is greater than 5. Remainder is equal to decimal divided by 2. And decimal is equal to decimal divided by 2. So let's take the remainder. Plus bit string. Interesting. Remainder. I didn't have to think about this one. Let me see. decimal is equal to 5. While decimal is greater than 0, which it is, remainder is equal to decimal, and that's the mod returns the remainder. When you do 5 divided by 2. 5 divided by 2 is going to give us 2 with a remainder of 1. So, remainder is equal to 1. Then, is taking decimal. It's going to equal to 5 divided by 2. And I'm trying to think what integer division looks like on that. I guess they got it listed right here, don't they? 2. So I guess it ignores the decimal. So that's 2. So that's where we get our remainder here of 2 and remainder of 1. And it tells us our binary. Binary is the last part here, which is our bit string. So it's showing how it's being built. So it starts out with a 1. Then, next pass, decimal's 2, which is still greater than 0. So remainder is equal to the decimal divided by 2, the remainder of it. So decimal's 2. 2 divided by 2 is equal to 1 with a remainder of 0. So that's where this next 0 comes from. And then decimal is going to equal to decimal. What is decimal? Decimal's 2 divided by 2. It's integer division, which is 1. And that's where the quotient of 1 comes from right here. And a remainder of 0. And then they're attacking that 0 we've just found on the front of the string. So then you take your remainder. Our decimal is still greater than 0. So remainder is going to equal to your decimal, which is 1 divided by 2. 1 divided by 2 is 0 with a remainder of, think this through, remainder of 1. And then my decimal is going to equal to my old value of decimal, which is 1 divided by 2, which is 0. Okay, I see how it's built now. See, interesting. I never have seen the coding for converting that way. When I teach that in class, I teach using a different technique. Okay. That shows how to run it. Okay. There's a quick way to compute the decimal value of that number. Octal and hex. Well, kind of the same thing. Same kind of algorithm. Okay, to convert from octal to binary. So they're not talking about going to decimal. They're talking about going from an octal to a binary in this case. Start by assuming each digit in the octal number represents 3 digits in the corresponding binary number. To convert binary to octal, you begin at the right and factor the bits in groups of 3 bits each. Interesting. This 111 here would be 7. This 011 would be 3. Remember, that's 2 to the 0, 2 to the first. So that's 2 plus 1 is 3. And this would be 4. Convert from hex to binary. Replace each hex digit with a corresponding 4-bit binary number. Okay. String methods. Python includes a set of string operations called methods that make tasks like counting the words in a single sentence easy. We got our length, which is how long a string is. But we have a sentence.split. And then a list of words. So let's take a look at that. test string equals the dog ran down the street. And list of words equals test string dot, and we're going to do a split. And then let me print list of words. Dog ran down the street. Splits them up. Now, split by default, I believe, goes to spaces. Let's see if I can remember the right syntax of this. List of words. It's either bracket or parentheses. 1. You might think it gives you the, but it gives us dog. Indexing starts at 0. So if I want to access this right here, the, I would start at 0. This is index 1, 2, 3, 4, and then 5. So if I want to print off a street, I'd have to do 5. Maybe not. 0, 1, 2, 3, 4, 5. Oh, helps if I actually spell it right. Capital O. It is case sensitive. There, print street. So again, if you parse it apart, you'd have to use that. CSV is a popular. Let's see if I can remember this right. Let's see. So I got 300, comma 400, comma 500, and nums equals test string 2 dot split, and I think then we put a comma in here like this. But let's see. Print nums. Yep, splits it apart that way. Remember that example I gave you earlier with the date 09/116/2018, and I said that the way we were picking apart wasn't very efficient. Well, date elements. Let's say, well, let's see, I have a date. Date string. You can bring that in through an input if you want. Actually, let me do that. Input date, the form, month, year. Let's try that again. Month, day, year. So then, after I bring that in, date elements are going to equal to date string dot split based upon the slash. Then I can say my day is equal to date elements 0. That's the first be in the list, and then our day, month. Let's try it again. Month, day would be date elements 1. In year would be date elements of 2. And so now I can print month, print day, and then print year. Okay, so if I run this, so left one of the Y's off, but 09/113 or 115 2018, you see it's now correctly split apart. Even if I run it and I put in 9/15/2018, so it isn't 2 characters for the month, it still works. So you have to figure out when you're working with strings which way the best way is to split them apart. What else does this tell us? For words, and okay, this is how you loop through all the words in a list after you broke it apart. Method behaves like a function but has slightly different syntax. A method is always called with a given data value called an object. So you got your object dot and then your method name. That's when we string is an object. And when we do date string and then you do a dot, that's when you can put split or whatever in there. There's other items. Split, I don't know if substring's one. Let's see. Substring, see how it's in yellow? Says view a complete list and documentation string methods by entering dir str into shell prompt, and then you enter this to receive documentation on an individual method. I don't know if I can come over here and type. No. Let's try to put it here. dir str. Run that. Is that right? dir str. Yeah, that was. Okay, it doesn't work here. But if we had a shell, we could do that. Here's what I've been referring to. You can split it apart based upon different characters. CSV is a common one, a comma. Comma separated value is what CSV stands for. Text file is a software object that stores data on a permanent medium such as disk or CD. When compared to a keyboard input from a human user, the main advantages of taking input data from a file are the data set can be much larger. Instead of you sitting there having to type in 10,000 numbers, you read the 10,000 numbers in from a file. Data can be input much more quickly with less chance of error. Data can be used repeatedly with the same program or with different programs. Using a text editor such as Notepad or TextEdit, you can create, view, and save data in a text file. Text file containing 6 floating point numbers might look like this. You got 34.6 space, 22.33 space, 66.75, and so forth. All data output to or input from a text file must be strings. Then the number must be converted to a string before output. But then after you bring it in, that's when you can convert it to a number. Or if you're writing it out, you take it from the number and convert it to a string. Okay, data can be output to text file using a file object. To open a file for output, you got F is equal to open, your file name, comma, W. W is for write. Then you see you got f.write, f.write, first line, /n, second line, /n. Those /n's go down the next line. So let's put first line on the first line in the file, and it'll put the second line on the second line. It's kind of weird how they have that done. And then you do, to close it, you do f.close. Sometimes if you don't close your file correctly, it does strange things in a program. The file method write expects a string as an argument. Other types of data must be converted to strings before being written to the output using str. Code segment illustrates the output of integers to a text file. Let's look at this because the formatting is incorrect again. Okay, that's right. We're going to write it to a file called integers.txt. And we're opening it for write. Okay, we're going to loop for count and range up to 500. Random.randint 1, 500 returns a random number between 1 and 500, integer-wise. We then want to write it out. And then at the very end, we want to close it. So the close should not be in the for loop. And this next line I want to do like this. And then I'll run it. And, oh, put file right here. And see, there's our random numbers. So we created a file. My dog getting ready to bark. Now reading text from a file, you're going to do open, and then you do R for read. Now from there, we're going to then read it line by line. After input is finished, read returns an empty string. So you got F is equal to open, and then you got your file name, comma, and then R for read. And for line in the file, you print a line. And this down here checks. Now this is not doing a loop, or no, while true, it is. So next code segment inputs lines of text with read line. And I think this is the entire item here. So let's see if I can copy that. Is it text? There we go. So we'll copy that. So that file we just created up there, we're going to read it in. We'll say the sum is equal to 0. Change these. Sum is equal to 0. We're for a line in F. We'll go through each line. Now I say each line. This is first line. This is second line. This is third line. So for each line in F, we're going to bring that in. And not sure if that's exactly necessary. We're going to convert to an integer, and then we'll add it. The sum is equal to the sum plus number that we just converted. And then at the end, we'll do our print. Okay, let's try that. Sum is that. Now, if I don't want to create the file over, I can comment these out. Otherwise, it'll create a brand new file each time with random numbers. So first time, we said our sum is 124675. I wasn't sure, by looking at this, if this one is necessary. Let's see if it is. No, it wasn't necessary. Because we only have one number per line, so we don't need to strip that out. Remember, that strips it out based upon like a space. I didn't think that was necessary in their code. What does it say? In Python, string representations of integers and float can be converted to numbers by using the functions int and float. So the int just converts it to an integer. Float would convert it to a float, obviously. Next code segment modifies the previous one to handle integers separated by spaces and or new lines. This is where the split is necessary. So if you got numbers separated by spaces, then you would use this. Here's our open, close, write, read line. So these are all the different items we can do in a file. You can open for reading, reading and writing, or appending, where you append lines on at the end of the file. Close it just closes it. The dot write outputs a string to a file. F.read inputs content as a single string. And this reads the entire line of text. Okay, accessing, manipulating files and directories on disk. The complete set of directories and files form a tree-like structure with a single root directory at the top and branches down to nested files and subdirectories. You can access any other file or directory by using a path name. When chain starts with the root directory, it calls it an absolute path name. When chain starts from the current working directory, it's called a relative path name. This is if you're writing some kind of program to loop through the directory structure. You don't know how many folders you'll have. Or directories. You could have 10. You could have 2. And so that's why using some kind of looping construct is an easy way to handle that. You see here, this is how you open a child file, parent file, sibling file. Child file, you have your child, which is the directory, comma, and then file name. Now that's based upon wherever you are. That's a relative. Now the parent file, the dot dot, what that's doing, let me think what that's doing. Yeah, I can't remember. That's interesting. Two dots or one dot. One of them goes clear back to the root. I think 2 dots goes clear back to the root because it does say parent. 1 dot, I believe, goes back just one folder. It's a one directory structure. I'd have to play with that to see, but since I don't have Python currently on this computer where I'm recording, then I can't. When designing Python programs to interact with files, it's a good idea to include error recovery. For example, before attempting to open a file for input, you should check to see if the file exists. Function os.path.exist supports this checking. Example, to print all the names of the files in the current working directory with a .py extension, you import os. That imports the code you can use. Current directory path is equal to os.get cwd, current working directory. So that gets your current working directory. List of file names, os.list directory, current directory path. That goes through and lists all the files there. Now, once you got all those files, then you loop through them with that for statement for names and list of file names. And if it contains .py in it, then you want to print it. I wonder what that would look like in this sandbox. That's interesting. Why to do that? Okay, let's run that. There. List of file names. Oh, their code's wrong. Surprise. Notice how we have list uppercase O. Don't go too crazy with variable names. The list. The list. Yeah, that's better. Uppercase this, lowercase this. Encrypt.py. That's the only one we have in here. Now, txt files, though, that should return integers.txt. If I want to print everything in that directory. 1, 2, 3, 4. Those are my files. Okay. Okay, here's the things you can do. You can change directory. You can get current directory. You can list the list directory. List directory. os.list directory. Oh, well, good plan. Why I said that is because this is wrong. It shouldn't be list space directory. It's this list directory. Okay, make directory. This creates a directory that returns a list of all the names in directory. Removes the file name path. Rename, you can change the name of it. Remove directory, path, and then a separator. Variable holds a separated character of the current file system. Exists, is directory, is file, get size, norm case. You can read all about those about that in the book. We're not going to really go into that in a whole lot of depth. But again, just so you can work with files that are currently out there. This comes in handy is if you got multiple text files you need to read in. And so you can go out there and find all the text files in a certain directory, read them all in, and import them into a database, for example. Well, that's the end of that chapter. All the rest of this is just reviewing what we just covered, which we've already talked about. So I'm not going to review on that. So let me go ahead and save this.